Okay, so welcome to the last lecture. So what I want to do is just do some overview of what we went through to make sure that everybody remembers basically from the beginning. Talk a little bit about the project and a little bit about what you can use this class material for. I mean, this is at least my view after talking to a few people who have been taking this class over the years, where they have been using it. And I think, so you don't have to just completely, the minute you finish the next quiz, completely forget about this everything and just move on. And if I have time, I will go and talk about current research. So if you're interested in compiler stuff, to give you a flavor of this is great what you learned, you actually got a good sliver of what compilers are all about. But what happens today in the research community, just touch on some of that. And hopefully we'll have some time for discussion and feedback. So this is where I started. We started saying we have these programs written in programming languages, and then microprocessors understand assembly language or object code, and we want to build a compiler in there to do that. And so here's a simple program I think we started with. So the first thing you can do is you can generate this unoptimized piece of code. That this actually came out of, I had a C code that I came out of GCC -0. And then the interesting thing is you can actually optimize and get rid of a lot of these redundant instructions and run it much faster. So, and I think we went from doing left, and now last project and this one, what you're working on, will end up more to the right. So in this thing, you basically build one from scratch. This is very interesting because many places where you go take compiler clause, build a compiler from scratch. But most of the time what you get, since this is such a large project, most places when you do teach a compiler course, you get a template. And saying, here's a template, you go fill out the things, fill out the optimizations, fill out parsing and stuff like that, and you basically go end to end. But what's missing there is most of the decisions are done for you. Okay, you don't get to design the instruction set, you don't get to design the intermediate representation, stuff like that. So what that means is, it's at the end of the day, you build a compiler, but you don't have idea what the hard decisions are. In this course, we basically, what I like to say is give you the rope to hang yourself with. Basically, we said it's all open, go do it. And what that means is, many times what happens is you do something, you make a decision early on, and then later you learn something, and then you say, oops, that was a bad decision, you have to go undo things. I mean, I guess a lot of people have that feeling. I think key thing is, it's a much harder course because of that. I mean, if you talk to your peers in other institutions, they might have done a compiler, but you probably had to deal with a lot of those decisions and all the bad decisions and recover from it. And the nice thing about MIT students is they manage to recover from those things and still keep going. And what that means is you understood some very basic stuff about building compiler. What are those hard decisions are? This is a lot more important because next time when you decide the compile, you actually have that knowledge because you actually had made the decision yourself. So I think that is key. So if you look at a compiler, what's a compiler? So you have a program, you do lexical analysis, you get a token stream, you do syntax analysis, parser, get a parse tree, do some semantic analysis, and have intermediate representation at the end. Do code optimization, we did it in the different order, but normally the code optimization comes, you have optimized intermediate representation, and finally a code generator that design assembly. So here's a question. Why do you need a lexical analyzer and a syntax analyzer? Why can't both be combined to one? Can you combine it to one? Can't you just have a grammar that read just characters and write your expressions and your tokens also with the grammar? Why did
naturally complex to have both of those into one?
Okay, that's one answer. I think that's a good answer. What else? Why can't?
You need to actually see the entire thing for actually decide what the correct.
Not really. I mean, LR one pass, you have to only see a little bit forward. You can still do that. What else? stopped.
I guess your syntax you can essentially deal with just tokens that might then you can different text representations.
Different?
Text representations.
Yeah. Okay. So here's my take on it. I think there are a few things. First of all, it's doable. Okay. But then I probably have to, I can't do just, if I do LR1 parsing, I look ahead one token. But now if I actually build, that gives me a lot of expressiveness in my language. But on the other hand, if now I actually have to build the token myself, I probably have to look forward a lot farther. So in there, so I might have issue about looking forward, because the minute I go there, I probably cannot make that decision. So there might be look ahead issues in there. Second, I think it's a little bit of historical reasons, because for a long time, parsing was a very computation heavy thing. I mean, to build these parse trees on large programs took a lot of time, lot of effort, very large tables and stuff like that. It was taxing programs. So by doing lexical analysis, you really broke, instead of having 100,000 characters, you only have 5,000 tokens. So it really reduces what you have to do. So in some sense, when you're really doing that, that breakdown was a good logical breakdown. But on the other hand, I think you can do both together, and there might be issues in there, but it's not, I don't think this is fundamental. So in lexical analysis, what do you do? You have tokens out of character string, and we dealt with regular expressions, and I'm just picking slides. I mean, you should know these things. I don't have to go and explain what a regular expression works. So this is just to bring those things back to your mind. And then we dealt with lexical analysis. So what we did was we defined regular expressions, and we built a non-deterministic finite automaton out of that, NFA. And then we came up with algorithms actually go from NFA to DFA. And then a DFA, you can go and build these tokens very nicely. So that was a really nice set of theory that we really use in compilers. Then we went to syntax analysis. So that means we start defining language using context-free grammars. Okay. So now we have a much more expressive thing. We can actually create these grammars for modern languages in there. And so here's a simple example where what you have is a bunch of this expression recognizer with minus, plus, and multiply, simple thing. And then we basically build a parse tree at the end. So you give a token stream, comes a parse tree at the end. So here's something a little bit new I'm adding in here that we didn't talk this time in the class. So if you look at different grammars, the simplest grammar is a regular expression. It's a grammar. It's a very simple grammar. And the biggest grammar is a context-free grammar. That basically says you can define from a context-free language how biggest thing you can define. Something a little bit less is unambiguous grammar. So you can write a context-free grammar that's basically ambiguous. You don't know, you have multiple ways of going that. And after that, you can create more and more restrictive sets by defining the technique you can use to identify that. So for example, if you do LR0 parser, there's a certain type of grammars it can recognize. Beyond that, it cannot recognize that. And as we go, you can keep building higher and higher things. So for example, if you're doing a modern programming language, you can come and say, okay, this language can be represented in a grammar that LR1 parser can parse. So you can have this multiple classes in there. And that's LRK, K could be any number. So that's why I said, if I actually start doing the entire tokens also using grammar, so probably you have to have a very high K in the LRK parser. So then basically we came up with this Parse Engine, which you give this table, and you have a state stack and a symbol stack, and then we just basically go streaming through the input data and look at the current symbol and look at what's in this stack, and we get a parse action given in the table. So you can have a generic engine given a parser table, and it will actually do the right thing. And of course, depending on a K, you have to actually look ahead to a little bit. And then we came up with a method to divide these parser tables. Okay, a lot of these things probably you can just completely forget about it after this class, because you are not going to come up with and write a YAC yourself to do a parser generator. You probably use a tool that actually do carp or something like that to do the generator. So, but the interesting thing to use that is, when it comes and say there's a shift reduce error, you at least know what it means. Instead of saying, darn, what does this mean? What do I have to do? Now you understand why it's saying there's a shift reduce error, shift reduce conflict, and then you actually can think through this and figure that out. And that's why learning this was interesting. And then we move into semantic analysis. Did a bunch of checks to understand the beyond context freeness. That means now you're actually putting context into these checks in there. Understand the types, uniqueness of variables. For control checks, you can do a bunch of things statically, and also dynamic things like array bound checks and null pointer checks that can be done. And after doing that, we translated into intermediate format that basically got rid of both the lot of language specific thing and also machine dependent part. So you came up with a very simple representation that just basically understand the program in there. And we basically did multiple layers. In the high level, that has more and more language specifics in high level IR, and as we get to low level, you eliminate a lot of this language dependent stuff. And finally, one before the last, we did code optimization. So key thing is, we want to get as close as possible to what somebody would write by hand, if we have good hand assembler. And also we want to start taking advantage of, in this project, exploiting architectural strengths and weaknesses. Strengths you take advantage of, weaknesses you're trying to avoid in there. And we did a bunch of things. I guess we are doing register allocation, and we are open to do other things in this thing. So, good. That's the entire semester, and in 10 minutes. So, you guys have actually amazingly built a good compiler, and from all the indication, every group managed to get a compiler working. This is amazing feat given how complex this project is, and knowing this is not the only project you guys are also working on. And this is really cool. I think this is a great achievement to get all those things done. And so now the fun part. This is optional, but I hope everybody participates. So what you want to do is figure out who has the fastest compiler, or at least who produces the fastest code in the compiler. And some years, people have really surprised me and from how well they do. And in fact, one year, they managed to beat GCC 03. And I didn't believe them. I said, it can't be done. But after looking at it, they actually did it. And so I'm like, wow. So people, I mean, I don't think they got any sleep for a few weeks. But besides that, I mean, so there's a lot of history behind it. So what I'm going to do is, it's for the first time, we are going to give the program 12 hours in advance. Main reason is I want to make sure you get all your optimizations working on this program. A lot of times it used to happen is I give it hour before, within the hour, beginning of the hour. And for most people, some optimizations didn't work. And actually, there are some years that the most aggressive compilers didn't really win because they couldn't get all the optimizations to work. They did a lot of things, whereas the few compilers that did some things that managed to be more robust wins. And this year we give, because of that, I'm going to give 12 hours. But this has a huge temptation. You look at the code and say, that statement there, it's a random number. I know what it does. I can actually replace it with this crazy thing, and I can get this to run so much faster. I don't want to see that. I mean, the thing is, if you win, then we'll actually examine what you compiled, and you have to explain the code and tell us how you achieve that. So don't try to do crazy things to make everything you do should be correct. Okay, it's provably correct. I mean, of course, you have to do correct transformation, but you should be able to prove that it's doable. Because there are a lot of times you look at the program and say, this transformation is correct, but there's no way for you eyeball and you can do that. But you should be able to, the compiler should be able to prove everything it does, in fact, is correct. So that's critical. So you can't look at the function and say, okay, I can do this, and it will work. That doesn't work. So you have to actually say that I go from A to B, and I in the compiling the code, not in your head, prove that going from A to B is correct. So I don't want that. People do that. So this is on the 14th at 11 a.m. And we'll announce a place and we'll provide some refreshments so we can have fun. And I think this is a fun time. Celebrate everybody's what they have done. So, little bit on So what's this all about? You spent a semester, a bunch of sleepless nights building a compiler. What did you gain? I think after you left this course, at many different levels, I think you have gained something. Most of you will be programming for a long time in your careers, and where you end up doing. And I think this whole course, you actually learn something in that. And there are a few things you might want to, some direct things that we learn in this language you can use. Some of these people you will be working with things like new architectures, either from designing architectures, building compilers. This large group of ECS type end up doing things like that, and then I think that will be useful. And very few of you, probably one or two, probably one in this class, if I'm lucky, will become a true compiler hacker and do a lot of it. But even if you don't do that, I think you'll learn a lot. So from an informed programmer's point of view, every program has to use a compiler. And with things like JIT compiler, things are much even more complex, more random, a lot of things happen. And for most of you until now, probably treated a compiler as a black box. It's there, you give a program, something comes out and it runs. And you have to trust it to do the right thing. And of course, compilers are programs, they have bugs too. And they have many implications for performance, debugging, correctness, that from now, you should be able to just not trust this black box to be working all the time and trusting it all the time. So what did you learn from 6035? You learned how optimizations work. And you also know why it didn't work. So assume you did something and you're expecting some result, and if it doesn't happen of what you expected, okay? And you can look at that and say, aha, this is not my fault because I fooled the compiler. Compiler got fooled because of that. It might be optimization problem. It might be a correctness issue. There might be issues in there that you, now because you understand what the compiler does, can actually decipher that. And another interesting thing is you should be able to read optimized code because you ran through the compiler and you're trying to debug, and there's this garbled bunch of assembly instructions and you don't know what's going on. And if you know the optimizer, aha, this is because it did common sub-expression elimination. I see that, and that is why this code looks like this. And I think for debugging purposes, especially if you're doing low-level debugging, this is very useful. And for example, some of the stuff I have been involved recently is basically trying to reverse engineer production code. So you don't have source, you have a binary, and you need to figure out what's happening in the binary. And they optimize code. And so you look at a piece of instructions and you say, what kind of C code would have produced that? And knowing optimization, say, aha, this is probably what it produced, and then after optimization, this is how it looks like. So knowing all this optimization, what they do, will be really useful when you're debugging. Second thing, a lot of people use this kind of knowledge is doing simple language extensions. Most of the time when you have a large programming project, one of the easiest abstractions you can do is do a very simple language abstraction. You are trying to read some complex input out there, XML file or some very complex. You are trying to define some kind of interface. You have a bunch of very high-level problem that, for example, you're trying to build an interface for people to use. And so you can say, okay, well, I can build a huge library, or I can define a very simple language. And nice thing about doing a language is you can easily add nice functionality in here. You can and check for semantics, and you can instead of having a language type thing where if people make mistakes, it's hard to understand. Building a simple language, you can actually give people warnings and guide people within the domain you want to be. And you can also help with optimization. So for example, if compilers show up in weird places. PostScript, it's a printer, but it's a language. It has optimization. OpenGL for graphics. XML. Okay, all those things, I mean, they don't sound like a programming language, but a lot of this actually is a language. There's a compiler and optimization. All those tool chain comes into play. And a lot of times, my feeling is as a programmer, at least when I was doing a lot of programming, every 6 months I came up with a problem. I said the best solution is trying to come up with a simple language. And I'll do the language, and I'll compile into that language. And because of that, I can have this interface that is a lot tighter than anything you could do with providing a Java interface or something like that. Because when you need to do that, a library, people abuse it, misuse it, do things, and in language you can actually have a much more better control, give good feedback, even do nice optimizations and stuff like that. And 6035 actually provided a lot of it. I mean, if you're doing a language, you need a Lex and a parser, and we actually gave you all those tools, and you learn to do that, and use intermediate representations, how to build that, you learn all those things. So next thing you might do is, if you are involved in more aspect of EE side or computer architecture side, every processor, there are many different processors out there. It's not just Intel x86 out there. There are hundreds of different processors. Your cell phone has one. Your watch has one. If you need to build a processor, you need to program it. And need to program it, you need some kind of a tool chain, probably C, Java, some kind of a compiler, or a JIT that actually maps into that. And it has implication in many different directions. So, for example, if you are more from the architecture side, if you are designing architects, you really need to have understanding about the compile aspects. Also, every architecture has to have coupled with the backend compiler that people targets that architecture. So, I think that's, from architect's point of view, there are a lot of cool things happening these days. I mean, I don't know how many of you are interested in that area. And people are looking at many different new architectures to build. However, if you are building architect, if you ever become architect, you have to have a really good notion of what compilers can do and cannot do, so you can actually balance off what happens in hardware and what happens in software, because compilers is the one come in the middle. So very good architecture is done by people who really understand the capabilities and limitations of a compiler. They can say, aha, I can get the compiler to do this, I don't have to do it in hardware. This is something that compilers can't do well, I will do it in hardware. So that limitation that people understand actually builds very good hardware. So knowing that is very important, especially architects. And this is what you learn. Excuse me. You learn what the capabilities and limitations of compilers, and you learn how to think like a compile writer. And also, every time you come up with a new architecture, you actually have to have a compiler tool chain. So there will be even the same amount of people actually building the compiler tool chain. And what that means is every architecture is a little bit different, and how to take advantage of that differences, generate the right code, generate optimal code, stuff like that. And in here, we learned a lot about that. We learned about intermediate representations, doing a lot of different optimizations, things like issues like assembly interfaces, register allocation issues, code scheduling issues, calling conventions, stuff like that. All those things come into play. So this, I think, interesting. What do I have to do? So all those interesting comes into play. I think there's a lot that you guys learn here. And then finally, if you are not sick of compilers by now, some of you might decide to actually become a true compiler hacker. Compiler is a very interesting field. It combines things like theory. A lot of things you do, things like if you look at lexical analysis, parsing, data flow analysis, a lot of very serious theory behind it. And there's a lot of algorithm, because everything in compiler is basically algorithmic transformation. And also the other aspect, compilers is probably one of the most complex piece of code that you have to implement. So there's a huge amount of implementation system aspect of it. So it really spans the entire spectrum in there. In theory, what we do is basically we have to develop these general abstract concepts and things like prove correctness, prove optimality. I mean, for example, interesting thing about something like Java these days. So when you get a Java piece of code and you are running it, the people working on saying, can you actually prove things about it? So instead of blindly run it, you give me a proof that I can actually verify that in fact it's not going to do a bad thing. How do you do that? Okay, they think of what's called a proof carrying code. So code comes with a proof of its goodness. It says, I will give you these guarantees and here's a proof, and you can go and verify. So there are a lot of those kind of things. It's very theoretical aspect for that. And also programming languages also, people are exploring a lot of different ways. I mean, we are used to this imperative paradigm, but there are object-oriented programming, logic programming, very different paradigms. To think, okay, it's like, I think 001 kind of touches some of it. So what has it been like? The very abstract concept of programming, and a lot of these come in this theory. And here's some example, parse theory, and we talked about lattices in data flow. There are a lot of theory behind it. In programming language, there are people doing languages just to evaluate this space in there. Algorithms. And most of the things we learn has huge amount of algorithms. And most transformation you want to do something, and you need to have algorithmic solution to do that. And we use things from all over the place. Graph theory, number theory, many different aspects come in. Optimization theory, all those things come in doing a lot of compiler transformation. And also, there's another aspect of it. A lot of times, a lot of transformations are heuristics because the theoretical solution is too complicated. So people come up with heuristics. So there's a lot of algorithmic aspect and also a lot of heuristic development aspect. So there's a huge range in here for people there are a lot of good compiler people who are really good algorithms people. Things like one recent optimization people have been working is called partial redundancy elimination. It's like combination of things like dead code elimination and constant propagation and common sub-expression elimination. Can you combine all those into one? Register allocation by graph coloring. So here's take abstract problem, map into really concrete algorithm. Things like most of these architectures have these multimedia instructions. How do you take advantage? How to compile to that? There's a lot of algorithms behind doing things like that. Come up with a compiler to do this automatically. And finally, implementation. Compilers are probably one of the most complex pieces of software out there. I was fond of saying for a long time, one only saving grace for compilers is it's deterministic. For example, operating system is deterministic. But JIT compilers just completely threw that out. Basically, now compilers, they are not even deterministic. So it's complex, and it used to be deterministic. You can replay things and get the same results, but JIT compilers, that entire concept is gone. And so we are basically, every problem of developing a large piece of software is in here. And any reasonable compiler has probably millions of lines of code. And the worst is most of other, for example, operating system comes in nice modules. Compilers, a lot of times, one gigantic big beast. It just all has to work with a very much more closer approximation than, because in operating system, there are very well-defined interfaces. Compiler is very hard. It's the same piece of code that we keep working on. So compilers, in some sense, has a huge systems problem in here. JIT compilers. Compilers have many. I say, one thing I say is the most lucrative compiler business in industry is actually all the databases. What's a database? It's basically a big query optimization engine. And also there's some operating system aspect of it to get consistency, persistency, and there are a lot of things you have to get. But one large aspect is a query optimization. So it's a compiler. A lot of, if you go to Oracle, it's a large group of compiler type people working on that. PostScript rasterizer, it's a compiler. I mean, every HP printer division has a bunch of compiler guys trying to figure out what's the best way to get from PostScript rasterize. It's a compiler file. So there are a lot of places, XML parsing, XML processing. A lot of things have very compiler oriented. So if thinking like a compiler hacker is very interesting in these things. So to be a compiler hacker, what do you learn in 6035? Basically learn everything. I mean, everything we did is also like put in this mind frame. So yeah, I have about 10 minutes before we do the HCAN review. And in that 10 minutes, I want to just switch gears a little bit and talk about current compiler research. So this is not going to be in the test, so don't worry about it and don't have more. So I will go through something very fast. So one thing I did was, if you're interested, I added a list of places where you find the most up-to-date compiler work. Most of them are in conference proceedings, because most compiler people don't publish in journals. With some areas it's all journals, and I listed different proceedings. So if you are really interested, you can, some of these journals are available on the web. You can search for it. I can look it up. This is not exhaustive list, and this is and depending on where your emphasis is, it's a very broad field. There are many other conferences and journals and places, but here's a subset. So what I want to do is switch from doing a class to give you a feel for what's happening in research. So I'm going to talk about a project that I'm doing in my group. There are a bunch of people out there sitting up there actually working on this project. So I give you a very quick glimpse of what it's like. So one thing I'm building in my group that's really exciting thing is this new language and compiler for streaming domain. Streaming means everything that from audio, video, everything in cell phone. A lot of applications today have data streaming through that. And how do you actually program that? So we have a language called Streamit, and it provides a very high-level abstraction for streams. So a lot of interesting things that drove us was most of these streaming applications are written in nice blocks, saying the block does something, feed that to the next block. And if you look at a DSP class, it's all in block diagrams. And the minute you write C, the entire blocks vanishes all over the place, and then it's a very ugly mess of C. And so we figure out, okay, how can you actually have a language that you actually have that representation? So another thing is, minute you go into language like C, those languages very hard to analyze, because everything in single memory, everything in single control flow, all that nice representation is gone. So in this language, what we have done is still maintain that representation. That gives us a nice ability to do a bunch of analysis. And then we build a compiler that to understand all those things and actually can do really cool amount of transformation. So let me give a little bit of a view of the language. It's kind of like Java. So here's a filter, here's a compute unit, and it has what we call init function, where when the filter starts, it just calculates some local ones. And then there's a thing called a work function that keep executing forever. So what happens is there's input data coming. This work function says I look at 2, peek 2, I remove 1 from the input and produce 1 into the output. So every invocation of that, I look at 2 elements, I produce 1 and consume 1, and the next invocation I will go up. So I keep doing this forever. And so that's very representative of a lot of stream calculation, because same thing keep happening forever. So this is only one filter. And then you can combine these filters from pipelines and parallelism for what you call split joins, and then there's a feedback loops when they have feedback. So by doing this, you can build this very complex, higher, larger graphs. So here's a very simple Streamit program. The only thing to observe here, the important thing is you have this graph representation and a text representation. We are almost one-to-one. You can look at a text and almost imagine what the graph is like. And what it says is you build this graph and you are instantiating these nodes into the graph, and then after this program basically will build the graph. And then when you say run, it keeps running forever. So it's not what this program does is running of this program basically builds this entire graph, and you can build very large graph. So there are some examples of a graph of a FM radio, vocoder that basically process separate amplitude and frequency of voice and do different processing in there. There's a GSM decoder in a cell phone. So these complicated graphs, each node is doing a bunch of computation. This is 3G, this next phone in there. And so we can build this graph. So the next thing I want to do is talk about some kind of optimization we can do there. So a lot of these are for DSP applications. So one thing we compilers do is we basically look at what people do by hand and automate it. So what a good compiler did not look at what assembly program is going to do by hand, trying to abstract it out and automate it. So in here what we did was we looked at what DSP engineers do by hand and tried to automate it. So one thing is DSP engineers look at is what we call linear state space filters. These are the ones that are input are basically linear functions, or outputs are linear function of inputs and some kind of internal state. And the state also keeps changing from a linear function. So in the DSP community, there's a lot of math around it, and what we try to do is come up with a way to automate that. So many DSP filters programs fit into this category. So what that means is each block is represented by, if you have input coming in and some local state, and local state is updated using the inputs and the previous state, and output is also calculated using the inputs and the state, and you have some matrices A, B, C, D defining what's going on. So interesting thing here is, assume you have a program in there. We came up with here's the representation of that program in this state. So A, B, C, D, you have some concrete values in here. And we came up with a linear data flow analysis to look at the program and get to the right. So you write, somebody write this, something looking like that left, and we automatically do the data flow analysis, and you can easily build the data flow equations and do that, and we end up in this right. So the nice thing is now when we get to this representation, so you have learned different representation. We learned one intermediate representation in this program, in this class, and here we have using a different intermediate representation. It's basically 4 matrices representing each of these filters. And the nice thing about that is, when you have that, you can do a lot of interesting optimizations using those representation. I will show one and show results for 2 others. So one thing you can do is combine adjacent filters. So assume the filter 1 is, to simplify, only use D. So output for the first filter, output is matrix multiplied by the input, and the second filter has the same thing. One thing we can do is, so the output of both is D2 times D1 times U, and you can calculate this a priori at compile time and come up with a combined filter, basically just do that. So instead of doing these 2 matrix separate things, I can just do a matrix multiplication, because D1 and D2 are basically constants. It's in the program, and I will do that matrix multiplication once and do that. So nice thing about here is, so if we have these 2 filters like that, and I can come up with this combined filter. And in the first one, for each output, you can have to do 8 floating point operations to get the output. In the second one, you only need to do 6 operations, because some of them are done once at the compile time. So I reduce the amount of operations you need to do. So by doing that, I can really eliminate a lot of computation. So this is an interesting optimization. And actually, if you do a lot more, the first this decimator basically eliminates one value, so it's only looking at one result. If the decimator eliminates a lot of values and only look at, because a lot of times in DSP algorithm, that's what it do, you downsample. You only look at every 100th value. If you go, you can almost eliminate 75% of all the computation. So neat. So you can do optimization, you get rid of huge amount of computation. So in fact, for a bunch of programs we looked at, so the first line is show the yellow, the light blue line shows what the results of the optimization I talk about. So most times you can eliminate 80% of the computation. So 80% is huge. Basically, at the end of the day, most of the computation is gone. So there are 2 other optimizations we did. The second one here is basically, lot of in DSP people go from time domain to frequency domain manually. We said, why don't we do it automate? Why do you automate that? So we look at the program and said, instead of doing all these things in time domain, we'll automatically go to frequency domain, do a simplified calculation, and come back to time domain. And it's a very, very tedious process to do it manually, because a lot of these matrices have to be transformed, a lot of weird end conditions has to be met. It's all done automatically nicely in the compiler, and we get a huge amount of benefit. And then we actually have programming, we have an algorithm to select what's the best transformations to do and get a very good performance boost. So here are the kind of things we do today. So for this very high level new domain, we are building a compiler that basically trying to automate the DSP engineer, because right now this is all done by some guy by hand, basically for each algorithm. So we are trying to automate that. So this kind of gives you a feel for what goes a few floors up here. There are some people here who are basically working on these projects as UROPs, and if anybody else is interested in working in these kind of projects as UROPs, at some point send me mail.